Good morning, everyone. Yeah, today we will continue to focus on magnetic things. And last class yesterday, we mainly focus on magnetic fields. And today we will will focus on magnetic forces. Yeah, just like electric. Yeah, we talk about electric fields. We talk about electric forces. And for the magnetism, yeah, we talk about the magnetic field and also magnetic forces. Yeah. Okay, let's start today's class. Let me share my screen. Okay, let's continue to talk about magnetic fields and forces. And last class, like I said, we mainly focus on magnetic fields, and today we will mainly focus on magnetic forces. Okay. And yeah, we talk about the goal for this chapter. Yeah, we need to learn about magnetic fields and how magnetic fields exert forces on currents and moving charges. Yeah, and we have already talked about the magnetic fields, and yeah, we will talk about like how magnetic fields exert forces on currents and moving charges. Okay, like this is today's goal. Like firstly, mm, okay, yeah. Firstly, let's review magnetism and magnetic fields. Yeah, and then let's try to understand magnetic fields exert forces on moving charges. After that, we learn like magnetic fields exert forces on current. Yeah, let's see. Firstly, on moving charges, and then the exert forces on current. And then we study magnetic fields exert torques on dipoles. Yeah, torques. And finally, we will explore magnets and magnetic materials. Yeah, this is what we will learn in today's class. Okay, let's begin. First, let's review what we have already learned about magnetism and magnetic fields. You can see we talk about that only certain materials called magnetic materials are attracted to a magnet. And the most common magnetic material is iron. And the magnetic materials are attracted to both poles of a magnet. And in this class, and in today's class, we will talk about why, like those like magnetic materials are attracted to both poles of a magnet. And yeah, and uh, uh, every magnet sets up a magnetic field in the space around it. Yeah, we talked about this in last class. If another magnet, such as a compass needle, is then brought into this field, the second magnet will feel the effects of the field of the first magnet. It's just similar like an electric field. Yeah, and yeah, we talk about how to use the right-hand rule to find the direction of magnetic fields. Yeah, you can see this is a like a right-hand rule of fields. Firstly, point your right thumb in I, yeah, in the current direction, and then wrap your fingers around the wire to indicate a circle. And your finger curl in the direction of the magnetic field length around the wire. Yeah, it's not difficult, it's easy. Yeah, you just need to use the right hand rule to find the electric fields. Yeah, we have practiced some, we have used some questions to practice the right hand rule. Yeah, and you need to remember how to use the right hand rule to find the magnetic field direction. Okay. Mm. Then we talk about how to calculate like a magnetic fields. Firstly, we talk about like a calculate like a magnetic fields from current, just a where. Yeah, you can see we use this equation and to calculate the like if a current in a long straight wire and then how to calculate the magnetic field. Yeah, we use this equation, and we know like this is the constant, and this is the current, and this is the for example, this point, it's just like yeah, it's just a distance from this point to the the center of wire, like that. Yeah, this is how to calculate the electric field from currents. And then we talk about oh yeah, from the long straight wire. And then we talk about how to, yeah, firstly we know like the currents can generate electric fields, and then we use this equation to calculate the electric fields. And this is for coil, and a coil is a stand of loops. It's just a one loop and just stand of them. And then this is for the equation for like calculating electric fields for coins, and this n is just like a number of turns. It can be one, yeah, from one to like many. Okay, and this is the constant, and this is like a current, and this is the uh, mm, like this is the radius of the loop of coin. For example, this is the coin, and this is the radius of the coin. That makes sense to you? Yeah. And also we talk about how to calculate the electric fields for like a solenoid. Yeah, we use this equation. Yeah, the solenoid is a stand of loops with a length much greater than the radius. Yeah, and then we use this equation in the and this is just the number of turns, and this is current, and this is length of the solenoid. Yeah, so we can use those equations to calculate the electric fields for different situations. Yeah, yeah, this one. Like this is just for a single straight long wire, and this is for like a coin a stand of loops, but this length, yeah, is small compared to the radius. Yeah, this is small for the radius. You can use this equation. And if the length is greater than the radius, yeah, it's much greater than the radius, you can use this equation. And that makes sense to you. Okay, let us talk about this section. Magnetic fields. Uh, okay. Yeah. I want to clarify one thing. Like last class, I may talk about like the call. This situation is just a one. Is just like a one single coil and stack them together. No, it's not like that. It's also like the uh, 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 aware, like they just occur. It's just like this one. Yeah, and but just the length is smaller than the length is smaller than the radius, and this is the same situation, but the length is much greater than the radius. Yeah, sorry, I just like didn't see it very clearly. Yeah, just want to clarify that. Okay, any question, just let me know. Okay, let's talk about the magnetic fields exert forces on moving charges. Yeah, okay. And you can like watch this video for like magnetic fields and forces to get initial ideas. Yeah, I will not play the video here. Okay. Yeah, actually, magnetic fields also exert forces on moving charged particles and on electric currents in wires. Yeah, I think it's obvious because you can see like the electric fields, and if one charge or some other like uh, some other electric things into the electric fields, there will be a force on that. Yeah, similar with the electric fields and the magnetic fields also exert forces, yeah, on moving charged particles and on electric currents in wires. Yeah, we will look at the results of the following experiments to illustrate the nature of the magnetic force on a moving charged particle. Okay, let's talk about that. Yeah, there are some experiments to talk about like the magnetic fields exert forces on moving charges. Here, there is no magnetic force on a charged particle at rest. Yeah, if like a charged particle at rest, there will be no magnetic force, even there is a magnetic field. But for like a still charged particle, there is no magnetic force. And also there is no magnetic force on charged particle moving parallel to a magnetic field. Yeah, if the charged particle moving parallel, you can see parallel, which means you can move to this direction or move to this direction. It's also parallel, and there will be no magnetic field. Okay, yeah, the magnetic field is zero, and as an angle, yeah, if there is an angle alpha here between the velocity and the magnetic field increases, the magnetic force also increases. The force is greatest when the angle is 90 degrees. The magnetic force is always perpendicular to the plane containing the velocity and the electric field. You can see here, if this is the like direction, like the particle, the charged particle moves direction, and this is the velocity, and this is the electric field, and you can see the force always perpendicular to the plane, to these two the plane generated like by these two vector, and no matter what's the angle, yeah, alpha yeah, is is what, and as alpha like increases, yeah, as the angle increases, the magnetic force is also increases. Yeah, this is like we can observe from the experiments. Okay, and as the experiments show, the magnetic force is quite different from the electric force. Yeah, there is no magnetic force if the charged particle is at rest or if it is moving parallel to the magnetic field. Yeah, but for the electric field, forces, it's not like this. That makes sense to you. Is that right? Yeah, if you like recall what we talk about like electric field, yeah, and forces, you will know. The force is always perpendicular to the plane containing velocity and the like electric magnetic field. Okay, and we determine the correct direction of the force using the right-hand rule for forces. Yeah, we also can use the right-hand rule for like forces, but this right-hand rule is a little different with the one we talk about in last class, and you will know how different. But it also call we also call it a right-hand rule. Yeah, there are two possible forces vectors that are perpendicular to velocity and magnetic field up from the plane. Yeah, use this one. Or down from the plan, this one. We use the right-hand rule for forces to choose the correct one. Yeah, sometimes you don't know which one is the right, but you can use the right-hand rule for this. And you then you can see, spread the finger of your right hand so that your index finger and the thumb point out from your hand as showing. Yeah, this thumb is it points the direction of the velocity. Yeah, that is like charged particle move direction, and this the index finger point out the electric field direction. And then this like a middle finger, yeah, will point to the force, the direction of force, yeah, direction of the magnetic force, yeah, that makes sense to you, yeah. And let me show my figure to you. You can see here, this is your right hand, yeah, just use your right hand, and this one, this thumb, and it's just like use your uh, like uh, direct to point to the velocity direction, like the particle move. Yeah, charge particle move. And this one, yeah, just point to the direction of magnetic field. And this one, yeah, this one is just the uh, magnetic forces. Yeah, that makes sense to you. Yeah, got it. Yeah, just like put out your hand and try do this. Yeah. Okay, let's continue. Mm, okay. Yeah. And sorry. Yeah, now point your middle finger so that it is perpendicular to your palm. As shown, it will point in the direction of electric magnetic force. Yeah, you can see as I just show it to you. Those three, if you use those three fingers and the thumb is point to the particle motion direction, and the index finger is pointed to the electric like electric field direction of electric field, magnetic field, sorry. And the middle finger, you will see it is like a point to the direction of magnetic forces, and you can see it is perpendicular to your palm. Yeah, if you use your right hand, yeah, you will know that. And you can see this right hand row is a little different with the one we talk about NASA class. And do you remember what is the right hand rule for the NASA class? Let us review a little bit. And this one is just the current direction. Yeah, the thumb is, and then you use your right hand to curl your finger and then find the electric field direction. Yeah, does it make sense to you? Yeah, so those two are different. Yeah, remember that. But we also call we call both like a right hand rule. Okay, let's continue. And in this case, you can see in this case, if you use the right hand rule, yeah, just put out your hand, and you will find the like a magnetic force is directed up from the plane. Yeah, you can see it's just like this. Uh, like this. Does it make sense to you? Yeah. This is yeah, I think this will be more like uh just exactly what we just show. This is like velocity direction, and this is magnetic field direction, and this is magnetic forces direction. Yeah, that makes sense to you. Okay, let me share again. Okay, okay, let's continue. And we can organize all of the experimental information into a single equation. Yeah, the magnitude and the direction of the forces F. Yeah, we use this symbol. Actually, it's just similar with electric force. Yeah. Also, we use F on that one. Yeah. We here we use this symbol to represent the magnitude and the direction of the magnetic force on a charged particle moving in a magnetic field are given by. Yeah, this we can use this equation to decide the magnitude of the force. And this is the magnitude of charge. And this is the spin of particle. and this is the magnetic field, and this is that angle between like a velocity and magnetic field. That makes sense to you? Yeah, we can use this one to decide the magnitude of the force, and use the right hand rule to decide the direction of the force. Okay, you can view this this video for like a magnet and electron beam. Yeah, I will not play it here. Okay, let's like check some questions. Yeah, the first one is the direction of the magnetic force on the proton is. Yeah, here you can see for this for this one, and we know like what's the direction of the magnetic field. Yeah, this one, am I right? For this point, it is this one. This is the magnetic field, and this is like a velocity direction. This is the magnetic field direction. So we use right hand rule. Yeah, please please use your right hand rule and right hand and use the right hand rule, and this we just use our thumb to point the to point the velocity direction, and use the index finger to point the magnetic field direction, and then the middle finger is just the direction of magnetic force. What is that? If you use and let me put my, I don't know if you can see my face. Can you? And let me, yeah, and this, and you will find out it should be what on of screen. Am I right? If you use your right hand like this, let me see. Yeah, so the answer should be on of the screen, and it is B. It is Z. Does it make sense to you? Okay. Let's continue. Yeah, the velocity and the magnetic field are perpendicular. Let me check. Yeah, are perpendicular in many practical situations. In this case, alpha is 19 degree, and the magnitude of the magnetic field simplifies to this one. You can see if alpha is 90 degree, and which means the sin 90 degree, what's the value? Is 1, am I right? 90 degree is 1. So this one should be removed, and then the equation become this one. That makes sense to you? Yeah. Okay. Let's try to talk about determine the magnetic force on a moving charge, the practical. Yeah, you can see know the direction of velocity. Yeah, this one, and the direction of the magnetic field. Yeah, this one, and find the angle alpha between them. Firstly, yeah, if you want to determine the magnetic force on a moving charged particle, the first thing you need to find the alpha. Yeah, you need first you need to find the direction of velocity and the direction of the magnetic field, and then find the angle alpha between them, and the force is perpendicular to the plane containing velocity and magnetic field. So the direction of the magnetic force is given by the right hand rule. Yeah, you can use the right hand rule. Yeah, we have already talked about it. Yeah, the step 2 is decide find the direction of a magnetic force, and then for negative charge, yeah, you can see we talk about it is just the positive charge here. Here is positive, and here is positive. Yeah, you can and for negative charge, the force is in the direction opposite to that predicted by the right hand rule. Yeah, so if you use the right hand for negative charge, if you find the find the direction, this finger, the middle finger direction is this one, which means the magnetic force direction should opposite it, so should to this direction. That makes sense to you? Yeah. The magnitude of the force is given by equation 20.5 or equation 20.6. Yeah, this is equation equation 20.5. This is for 24.6. Okay, and let's based on this tactics box, let's try to resolve some questions. And the diagram shows a top view of an electron beam passing between the poles of a magnet. The beam will be deflected. Yeah, you can see. Firstly, let's this is the velocity direction. Am I right? Yeah, sorry, you don't see that, am I right? This is the direction of velocity, and for the like a magnetic field, what direction? Do you remember what's that? It should from what? From N to S. Am I right? From north to the south. Does it make sense to you? Yeah. If you remember what we have talked about in last class, then you will know that. And then use right hand rule. Yeah, use your right hand, and the thumb should point to the velocity. Am I right? And the like index finger should point to the magnetic field direction. And then you will find the index figure is out of the plane of the figure. Am I right? But you can see this is electron, which means this is negative charge, am I right? So it should be opposite your like middle finger. So what is it? It should be into the plane of figure. Does it make sense to you? And let me show it to you. Yeah, it's just like this. That makes sense to you? Yeah, and you can see this is just a point out. Yeah, point out the plane of the figure. But you can see it is electron. Yeah, so which means the direction of magnetic force should be opposite to this one. So it will be into the plane of the figure. Does it make sense to you? Okay. Yeah. So which means the right answer should be what? D. Does it make sense to you? Okay. Yeah, any question, just let me know. Okay, let's continue. Like let's talk about this example, like Earth's magnetic field and a digital compass. Yeah, your smartphone probably has a built-in digital compass. There is no actual pivoting needle, of course. Instead, a sensor in your phone detects the Earth's magnetic field by the force it exerts on electrons moving in a conductor. The figure shows one of these electrons moving to the right when the Earth's field points in the direction shown. What is the direction of the magnetic force? Yeah, for this one, you can use the right hand rule. But just remember, because this is electron. Sorry. This is electron. It's negative, so it should be opposite your like middle finger. The direction of your middle finger. Does it make sense to you? Yeah. And you can see like this figure. Yeah, shows how right hand rule for forces is applied to this situation. Yeah, because the electron has a negative charge, the force is into the page. Yeah, because you can see your middle finger is out of the page, but it should be opposite this direction, so it is into the page. Yeah, and you can if for the right hand rule, you point your right thumb in the direction of the electron's velocity and your index finger in the direction of magnetic field. Bend your middle finger to be perpendicular to your index finger, and your middle finger, which now point out of the page, is the direction of the force on a positive charge. But the electron is negative, so the force on the electron is into the page. Does it make sense to you? Yeah. Okay, this is now difficult. you just use your right hand right hand to find the right direction, and then you will find the direction of magnetic forces. Okay. Yeah, you can see the force is perpendicular to both the velocity and the magnetic field, as it must be. The force on an electron is into the page. The force on a proton would be out of the page. Yeah, we talk about this. Yeah. Okay, let's continue. Okay. Yeah, like let's talk about the path of charged particle in magnetic fields. Yeah, when we studied the motion of objects subject to a force that was always perpendicular to the velocity, the result was circular motion at a constant speed. For example, a ball moved at the end of a string and moved in a circle due to the perpendicular force of the tension in the string. Yeah, for a charged particle moving in a magnetic field, the magnetic force is always perpendicular to velocity direction. So it causes the particle to move in a circle. Yeah, actually, this is just like a rule, like a fact, like the circle motion at a constant speed. If the force direction is is perpendicular to the velocity's direction, and then this object will move in a circle. Yeah, so this is just a rule. Yeah, a fact like that. So for a charged particle moving in a magnetic field, the magnetic force is always perpendicular to this velocity direction. So it causes a particle to move in a circle. Okay, let's talk about more about this. And you can see a particle moving perpendicular to a uniform magnetic field undergoes uniform circular motion at constant speed. Yeah, this is just a special case. We know, like in this situation, yeah, this is like this symbol. What's this symbol mean? Yeah, we talk about in last class, which means last class, yeah, which means it goes into the plane, goes into the surface. This plane. That makes sense to you. And this velocity is this direction, which means the velocity is like a the velocity direction is perpendicular to the magnetic field direction. That makes sense to you. Yeah, and which means the alpha equal what 90 degree. Yeah, this is a special case. Okay, and in this case, and since the like a magnetic field is a uniform magnetic field, so which means there this particle will undergo the uniform circular motion at a constant speed. Yeah, the speed will constant, and it will the trace. Yeah, it should be a circle, and then the like a force is always like a perpendicular with the velocity direction. Yeah. Okay, let's continue. In chapter 6, yeah, if you I think you guys have already finished the college physics 1. Yeah, in chapter 6, we found that the circular motion requires a force directed towards the center of the circle with magnitude. This one. Yeah, if a object have this trace, like a circle moves in a circle, and then it should have a force directed toward to the center of the circle and with magnitude this one. Yeah, and we also know, like for a charged particle moving in a magnetic field, the force is provided by the magnetic force. Yeah, this is the equation we just talked about. And here it should be sin alpha, but alpha is equal 90 degree in this situation. That makes sense to you? Yeah. So which means this part should be removed, so we can get this equation since the force should equal this one because provided by the magnetic force. Also, it should equal this one because the chapter 6 have this rule. 6 tell us if object moves in a circle and the force should have this equation. Yeah, so which means those two equal with each other. Yeah, those two. Does it make sense to you? Yeah. And then from those equation, we can get this one. We can get this equation. Yeah. Yeah. And you can say solving for R. Yeah. If you solving this one, like a QVB equal MV squared divided R, which means R equal what? MV squared divided QVB. And then there is a V, there is a V, and you just remove one, and which means MV divided QB. Yeah, does it make sense to you? So just just using this equation. Yeah, using this equation, you can we can find the radius of circular orbit for a charged particle moving in a magnetic field. Yeah, this one. And if we know the particle mass, and if we know the particle velocity, particle charge, and magnetic field strength, and then we can know how big circle this particle move. Does it make sense to you? Yeah, this R is just the radius of this circle. Does it make sense to you? Okay, let's continue. When a particle's velocity is neither parallel nor perpendicular to the magnetic field, the net result is a circular motion due to the perpendicular component of the velocity coupled with a constant velocity parallel to the field. You can see here, if if the angle between the magnetic field and the velocity is not 90 degree, is any degree alpha. Yeah, for this one. And then you can break the velocity into components parallel and perpendicular to the field. The parallel component will continue without charge. Yeah. Yeah, and I think, do you remember the beginning? We talk about if sorry, the internet. Yeah, if the there is no magnetic force on a charged particle moving parallel to a magnetic field. So for this situation, sorry. Yeah, for this situation, the parallel component will continue without change because it will not have a magnetic force. Only the perpendicular component work and make the circle, make the particle move in a circle. Does it make sense to you? Okay. And this is a top view, shows that the perpendicular component will change. Yeah, the parallel component will continue with no change. Yeah, and only the perpendicular component will change, leading to circular motion. Does it make sense to you? Yeah, this is just the magnetic field direction, which means it is out of the plane, and this is the velocity direction, and this is yeah, and this should be the magnetic force direction, and then this particle will move like this. Does it make sense to you? Okay, let's continue. The net result, yeah, is a helical path that spirals around the field length. Yeah, because you can see, because it although the parallel component will not will continue without change, which means it has a direction. It has a parallel direction, and then which means it will like a circle but up. Does it make sense to you? Yeah. Does it make sense to you? Yeah, it will like have the same direction to the like a magnetic field. For this one, it should goes to go out of the plane, and then which means the net result is a helical path that spirals around the field length. If there is no like a parallel component, it will just like a circle, circle, circle. But there is like a parallel component, yeah, and then it will like go to the go up and along the like a magnetic field direction. Does it make sense to you? Yeah. Okay. Yeah, you can see that's the reason why like the aurora like come out. You can see the high energy particles stream out from the sun in the solar wind. Yeah, some become trapped in the Earth's magnetic field. The particles spiral in helical trajectories along the Earth's magnetic field lines. When they enter the atmosphere at the poles, the arrows L the the ionized gas creating the aurora. Yeah, because you can see if there is a magnetic the Earth's magnetic field leads the particle into the atmosphere around the poles. Then they will run like do a helical move in helical trajectories, and then you will see this like situation. Yeah, it will go up like that. Yeah, does it make sense to you? Okay, and let's check this question. A beam of positively charged particles passes between the poles of magnetic as shown in the figure. The force on the particle is noted in the figure. Yeah, this is the force. This is the force direction, which means it is to this. This is the force direction to this one. Yeah, and sorry. Yeah, this is like a magnetic force direction, and yeah, and the force on the particle is noted in the figure, and the magnet's north pole is on which side, and the north pole no, south pole on which side. And you can see the velocity direction is into figure, which means it's going to the like a plane. Yeah. So then what we can use, we use, yeah, notice this is a proton, so it is a positive. So just use the right hand rule, and you just use your like thumb point to the velocity direction, and use your here, and this direction should your like a middle figure direction. That makes sense to you? Yeah, so it should be like this. Yeah, and just remember this like a magnetic force should be your middle figure direction, and then you can see your like index figure is pointed to what to left. That makes sense to you? So which means this is your magnetic field direction. And we know like the magnetic should from N to S. That makes sense to you. So which means the north pole should on which one? On right. And the south will be left. And so the answer is B. That makes sense to you. Yeah, you just use the right-handed rule to do that. And let me show it to you. Yeah, this one. Yeah, this is your like direction of the velocity, and just remember. And for now, this your middle like figure. It is to the to up. Does it make sense to you? Yeah. So which means this one, yeah, is pointed to left. Yeah, from right to left. Yeah. That makes sense to you. Yeah. Just use your right hand to find the like usually you find the direction of magnetic forces, but here you find the direction of magnetic field, but it's the same thing. But just remember the thumb finger represents the velocity direction, and the index finger represents the magnetic field direction, and the middle finger represents the magnetic force direction. So don't mess it up. Yeah. Okay, let's continue. Let's check this one. The direction of the magnetic force on the electron is, you can see this one, which means here, like the velocity, the magnetic field, the direction of magnetic field actually in this point is just this direction. Does it make sense to you? So which means the velocity direction and the magnetic field direction is parallel. Yeah. So which means it should not, there is no magnetic force. Yeah, we talked about it at the beginning and also talk about just now. Yeah, so the magnetic force is what, 0, because it's parallel. The velocity direction is parallel with the magnetic field. That makes sense to you? Yeah, so the answer should be Z. Okay, let's continue to talk about this one. Yeah, which magnetic field causes the observed force? Yeah, I think this one is also like easy. And here we know this is velocity direction and the magnetic forces, yeah, out of the screen, which means this is thumb figure and this is middle figure, and what we need to find out the magnetic field direction, the index figure direction. But pay attention here. This is electron. It is negative, which means the electric field is out of screen, which means the middle figure should point into the screen. Does it make sense to you? You need to pay attention to that. The positive and negative charges are different. Yeah. So which means the thumb should point this to the like a down left, and the middle one, the middle figure should into the screen. That makes sense to you? So then you will find the magnetic field direction. It should be like this. Sorry. Let me show it to you. Yeah, it should. Yeah, this is just like the velocity direction, and this middle figure is pointing into the screen because the forces, the magnetic force is out of the screen, but this is the electron is negative, so it should be opposite. Yeah, so this direction is like a magnetic field direction. So it should be which one? C. That makes sense to you because it's up, right, up, left. Yeah, up, left. That makes sense to you? Yeah. Okay. Yeah, it should be, the answer should be C. Yeah, that makes sense. Okay, let's check this question. Which magnetic field, if it is a correct strength, allows the electron to pass through the the charged electrodes without being deflected? Which means here you can see there is a capacitor, yeah, and which means that there is electric fields. The direction should be like this. Am I right? And if we want this electron pass through this electrical field and without being deflected, which means we need to create it should be an extra electric magnetic field. And then, I'm sorry, think there is a electric field from the positive to the negative, and here this is a electron, yeah. So which means it should go up because it will it should be attracted by the positive like charges. Yeah, because this is an electron, it is negative. Yeah, does it make sense to you? So it will be attracted to this direction, and which means if there is no other like thing, no other effect, these electrons will move to upward. Yeah, but for now we need to let him to go straight, which means we need to give this electron an extra force downward. Yeah, does it make sense to you? Down a little down. So which means the electric force should be down. That makes sense to you. So then we can use the right hand rule, and yeah, you can see your thumb to the like to the uh, velocity velocity like direction, and your like middle finger should be. But here you can see this is electron. Yeah, so this actually this question is a little tricky. So it's electron. So which means your like middle finger should opposite to the your like to the magnetic force. So the your middle finger should up. That makes sense to you. So which means it should the if you use the right hand rule, and you will find the index finger. It is pointing into the plane. It's just like this. Yeah, this is the direction of velocity, and this is the this yeah, this middle figure is your like actually is opposite the magnetic force. Yeah, because it is electron. Yeah, so this one is the magnetic field direction, which means it should point into the plane. And then which one is the right thing? It is E, am I right? Yeah, let me. It should E because this one is just point into the like a plane. Does it make sense to you? Yeah. Okay. So the right answer should E. Yeah, so this one, actually, this question is a little trigger. Firstly, you need to find the electric field. Yeah, there is electric field. Then you need to judge like what's the electric force. Yeah, because you can see this electron, so the electric force uh, should up. Yeah, and then you need to if you want this electron to pass just without being deflected, you should there should be a electromagnetic force, yeah, to let him go down, yeah, because otherwise he will go up, and then this is a magnetic force, and because this is electron, which means if you use the right hand rule, your middle finger should up, and then you can find the magnetic field direction. Yeah, it will be E. So yeah, this one is a little tricky. Okay, let's talk about this one. A proton is short straight at the center of a long straight wire carrying current into the screen. The proton will, yeah, you can see. This is a long wire into screen, and which means when firstly, let's find out the magnetic field because how can we find the magnetic field? Yeah, use the right hand rule, but in last class, yeah. So you use your right hand and your thumb should point to the current direction, and then your like figure, your all your figures should curl, and then you will find the direction of the magnetic field. Yeah, just point to the uh, current direction, and then this one will be your like a this one will be your like a magnetic field direction, and you can see it should if you use your right hand, it should be the direction should go up. Yeah, try to do that. Yeah, if you use your right hand. And then you can see you now you know the electric field direction, you know the velocity direction, yeah, and it is a positive charge, and then you can use the right hand rule to find the magnetic force direction. Yeah, magnetic force is just like how this charge move to the like what direction this charge move. And you can see if you use the right hand direction and the thumb pointed to the velocity direction and the index figure is just like the magnetic field, and then the middle figure is the magnetic force direction, and it should be out of the screen. Am I right? Out of the screen. So which one? Yeah, it's just like this. Yeah, this is just the like velocity direction, and this is the magnetic field direction, and this one, yeah, you can see it just point to me. Yeah, and which means it will what? Which one? I think that will be easy for you to choose. It will hit the whale in front of the screen because it will out of the screen. Am I right? Yeah, does it make sense to you? Okay. Okay. It should be. Yeah. Yeah, this is just the like magnetic field direction, and then you use the and you use the like a right hand rule. It should hit the whale in front of the screen. Okay. Let's talk about the psychology. The cyclotron. Yeah, the medical imaging technique of like positron emission thermography. We call it PET. I don't know if you have you ever heard of this before. It's used to make images of the internal biological activity of the body. Yeah, cyclotron fires energetic protons at these atoms O8, like atoms in water, creating F80, which is needed for PET. Yeah, you can see this like a cyclotron. Yeah, technologies can help us to do some medical to form some medical imaging and related to PET. Yeah, this is an application for like a magnetic field and magnetic forces. And you can see here, a cyclotron consists of an evacuated chamber within a large uniform magnetic field. You can see this is a magnetic field direction. And inside the chamber are two hollow conductors called disks and separated by a small gap. You can see here, like this, and by a small gap. Yeah, this is one D. This is one D. This is another D, and two hollow conductor and separated by a small gap. And the T to accelerating the protons lies in the oscillating electron potential applied between the Ds. Yeah, you can see. Okay, like for a cyclotron, and the key is to accelerating the protons lies in the oscillating electron potential applied between the Ds. And the oscillating electron potential creates a strong electric field in the gap between the Ds, which accelerates the protons passing through the gap. The protons travel in a circular path in the magnetic field when they reach the opposite gap, and the potential has changed signs, so the electric field again accelerates the protons. The protons' orbital radius must be proportional to their speed. So as they increase in speed, they move toward the outer edge of the magnet, where they eventually exit as a high energy beam that can be directed to an O80 target. Yeah. So this is how cyclotron to use the magnetic field to get to use the like a magnetic field to like accelerate the materials and then fire the energetic protons at this one at 0.8 atoms water and creating F18s, which is needed for PET. And this is how cyclotron is used for like PET and for medical imaging technology. And this one use the like a magnetic field and magnetic forces. Yeah, this is an application. Yeah, you just know this. Okay, let's talk about after we talk about the cyclotron, and let's talk about this example. Yeah, this is just be ready. What do we talk? Why we talk about those things? Because we want to prepare for this example. Yeah, it takes a proton with a kinetic energy of 11 MeV to efficiently change all 80 nuclei into F80 if the magnetic field inside the cyclotron is 1.2 Tesla. We talk about 1 Tesla. Actually, it's very like has very it's quite big. That makes sense to you. Yeah, we talk about the NASA class. What is the radius of the proton's orbit just before they exit the cyclotron? Yeah, actually, you can see the equation like 24.8. Yeah, it's just this equation R equal mv divided qb. So yeah, this question just let us to calculate the radius of protons orbit. Yeah, so this is, and we use, yeah, we can easily to think use this equation. Yeah, this equation relates the radius of a charged particle's orbit to its speed. We can find the speed of the protons from their kinetic energy. To do so, we will first need to convert their energy from EV to G. Yeah, actually, yeah, we have already talked about how to like convert it. Yeah, like this is just one EV. It's just this G. So it has this EV. So because there is a M, so it is 11 multiple 10 power 6. So then the total like kinetic energy is this one. And then we use the kinetic, we know like the kinetic energy particle is this one. Yeah, we talked about it before. And so the proton speed, yeah, for this, using this equation, we know like V square equal what? 2K divide M, right? And then V equal what? Square, right? So, which means the velocity should equal this one, and then we calculate the velocity, and then we use this equation. And we know the mass for the particle. Yeah, actually, you can easily find this in our textbook, and this is the mass for the electron. Yeah, for the yeah, proton. Yeah, this is not electron, it's proton. It's a positive. Yeah, and which means we can easily find the mass for the proton, and also the velocity we have already calculated, and the charge, yeah, because it is one proton, so it's just this positive thing. And then the magnetic field, we have already know that, and then we can calculate the radius. It is 0.4 like a meter. It's big, am I right? Yeah, so it's just like this one. Yeah, this woman next to the cyclotron in the picture is roughly 2 meter tall. So 0.8 meter diameter. Yeah, because the R is 4.4, and which means the diameter is 2 times. So it is 0.8 meter diameter, like diameter. For protons orbit as it exists the cyclotron seems reasonable. Yeah, does it make sense to you? Okay. Let's talk about the other topic. We call it electromagnetic flow meters. Yeah, and we will talk about what's it. And an electromagnetic flow meter is a device that can be used to measure the blood flow in an artery. Yeah, it applies a magnetic field across the artery, which separates the positive and negative ions in the blood. Yeah, you can see. Yeah, this is just like the electromagnetic flow meter. Yeah, it has the north pole and the south pole, and this north pole south pole is generated like a magnetic field, and this magnetic field cross the artery, and which separate the positive and negative ions in the blood. Yeah. You can see the flow meter measures the potential difference due to the separating of the ions. Yeah. And the faster the blood ions are moving, the greater the forces separating the ions become, therefore generating a higher voltage. Therefore, the measured voltage is proportional to the velocity of the blood. Yeah, so this is like how the electromagnetic flow meters can be used to measure the velocity of the blood. You can see because is we can here this is the uh, uh, north pole, and this is the south pole, and then this is a magnetic field, and here then the positive and the negative should be opposite. Yeah, should be separated. Sorry, separated, and then it will have a voltage difference. Does it make sense to you? Yeah, it's easy to understand. We have already learned. Yeah, because this is there is a positive. For example, it is one volt, and this negative 1 volt. So there should be a difference. That makes sense to you. So we can use the velocity to like a velocity meter, yeah, voltmeter to measure the velocity, and this velocity actually is proportional to the velocity of the blood. Yeah, then we can use it to get the velocity of the blood. Yeah, this yeah, you can see this two is an end view shows that the magnetic force on the positive ions is to the right, and that on the negative ions is to the left. You can use the right-hand rule to verify that, and the result charge separation leads to a potential difference that can be measured between two electrons. Does that make sense to you? Yeah, this is an application for like how to use magnetic field, magnetic things to measure the velocity of the blood. Okay, you can do this by yourself, like magnets and television screens. Yeah, the image on a cathode ray tube television screen. Actually, I'm not sure if you can find this kind of. Yeah, actually, this kind of TV, you for now you can seldomly find it. Yeah, but yeah, we just talk about it, and you can like know. Yeah, this kind of TV can do this experiment. The image on a cathode ray tab television screen is joined by an electron beam that is steered by magnetic fields from coils of wire. Other magnetic fields can also exert forces on the moving electrons. If you place a strong magnet near the TV screen, and the electrons will be forced along altered trajectories and will strike different places on screen. Then they are supposed to they are supposed to, producing an errand of bright color. Yeah, the magnet can magnetize internal components and permanently alter the image. So do not do this to your television. Okay, yeah. Actually, I think you can. For now you it's very difficult for you to find this kind of television. So I don't think you can do this by yourself. Okay, yeah, but you just know that. Okay. Uh, let's talk about the other important topic. Magnetic fields exert forces on currents. Yeah, and we have already talked about the magnetic fields on moving charges. Yeah, magnetic fields like exert forces on moving charges. And then let's talk about magnetic fields exert like forces on currents. Okay. We learned that the magnetic field exerts no force on a charged particle moving parallel to a magnetic field. Yeah, we talk about this. If a current carrying wire is parallel to a magnetic field, we also find that the force on it is zero. So yeah, it's similar. You can see there is a force on a current carrying wire that is perpendicular to a magnetic field. Yeah, you can see this magnetic field should into the plane, and then the current, otherwise it is up or down, but it's perpendicular to the magnetic field. So note that the magnetic field showing in the figure is an external field created by a permanent magnet or by other currents. It's not the field of the current I in the where. Yeah, just like this is now the magnetic field like generated by this current. It's just like from other like by a permanent magnet or other currents. That makes sense to you? Yeah. Okay. Yeah, if the wire carries a current, the magnetic field will exert a force on the wire. Yeah. That makes sense to you? Okay. Let's continue. And the direction of the force on the current is found by considering the force on each charge in the current. And the right-hand rule for forces applies to currents in the same way. Same way it does for moving charges. Yeah, like for the magnetic force on a current, we also can use the right hand. And you can see for the moving charges, and this is just like the velocity direction, and for here it's the current direction. Yeah, the right hand rule for forces applies. Your thumb should point in the direction of the current. Yeah, then you can use the right hand rule to find the magnetic force direction. Yeah. Okay. The length of the wire L, the current I, and the magnetic field B affect the magnitude of the force on the wire. Yeah, so we use this equation to calculate the magnetic field, not magnetic force on like a wire, on a current, yeah, on a wire. Yeah, okay. So this is just the current, and this is just the like the uh, with the length of wire, and this is the magnetic field. Just remember, this magnetic field is not generated by the wire, and it's just the outside, yeah, internal like magnetic field. Yeah, this is the angle, like this is a magnetic field, and this angle is the angle between the magnetic field and the current. Okay, and when the wire is perpendicular to the field, which means the alpha is equal 90 degrees, so we can remove this one because it's equal 1. It's equal 1. Does it make sense to you? Yeah, and then we can get this equation. Yeah, and this is how can we get how we calculate the magnetic force on a current, and you can also review these videos for like current carrying wire in magnetic field. I will not play this video here. Okay, let's review some quick check questions. Yeah, the horizontal wheel can be levitated, held up against the force of gravity if the current in the wheel is, which means this question that this is the force of gravity and it is downward and which means if we want to this wheel be levitated, which means there should be a force upward. Am I right? And here, and this one asks us the current, and which means this is F, like magnetic force direction. And then we just use the right hand rule to decide the current direction. And yeah, then you can see you just use the index figure to the because the magnetic field direction is just pointed into the screen, and the magnetic force is up, and then you can see the current is the direction of your thumb, and so it is from left to right. Does it make sense to you? It's just like this. It's just like this. Yeah, and this is just the magnetic field direction, and this is the current direction, and this is the force direction. Yeah, does it make sense to you? Yes, so the answer should be B, from left to right. Yeah, just use the right hand rule. Okay, let's talk about this example, like finding the magnetic force on a current carrying wire. Yeah, scientists have studied the aerodynamic forces generated by a flying insect by tethering it to the center of a taut horizontal wire. As the insect flies in a wind tunnel, the insect exerts force on the wire that a researcher can detect by measuring the wire's deflection. To calibrate the wire, a known force must be applied to it. This is done by passing a current through the wire, where it is positioned in a magnetic field that is perpendicular to the wire. The researcher requires the force on the wire to point upward with the magnitude of this one. Yeah, and let's see what's the question. The researcher requires the force on the wire to point upward with a magnitude of this one. And yeah, the length of the wire that is in the field is this one, and the wire carries a current of 30 MA from left to right. What direction and magnitude of magnitude of magnetic field will provide the necessary force? Yeah, because the magnetic field is perpendicular to the wire, we will use equation 24.10 to calculate the force. Actually, let me show you which one we can use. Sorry. Yeah, this one. This equation we can use. Yeah. Okay. Yeah. Like, and the right hand rule for forces will be used to find the direction of the field. Okay. Yeah, a stretch of a situation is shown in this figure. Yeah, in which the magnetic force on the wire is showing point up. Yeah, this is the magnetic field, magnetic force, and as required, we have assumed that the current is directed to the right. Yeah, we assume, like we have assumed the current is directed to the right. So then we can find use the right direction, use right hand rule to find the direction of electric magnetic field direction. You can see this is your thumb direction, and this is your middle finger to point to the force direction, and then the index figure is point to the magnetic field direction is into the plane. That makes sense to you? Okay. Yeah, as shown in the figure, the right-hand rule for forces showing that the direction of the magnetic field is into the page. Solving the equation 20.10 for the magnetic field, yeah, we can use because the 20.10 is F equal I L B, and I is current, L is the length, and B is a magnetic field. And then we can calculate the B. F divided IL. Yeah, we put F here and I here and L here. And we can calculate the magnetic field is 0.28 Tesla. Yeah, table 20.1. Yeah, that table. Like a different magnetic magnets have different like a magnetic field. Yeah, it's a reasonable field for a laboratory magnet. Yeah, laboratory magnet. Okay. Yeah, this just use the right-hand rule to find the direction and use the equation for like a force. Yeah, you can see if you know the force and then if you want to calculate the force and you know those three. If you want to calculate the magnetic field and you know those three, and then you can calculate it. That makes sense to you? Okay, let's continue to talk about the forces between currents in the because a current produces a magnetic field, and a magnetic field exerts a force on a current. It follows that two current carrying wires will exert forces on each other. That makes sense to you? Yeah, a wire carrying a current I1 will create a magnetic field B1. We suppose, yeah, we just assume. And like a second wire with current I2 will experience the magnetic force due to the wire with current I1. Yeah, you can see here this is I1 and this is B1. Yeah, using the like right hand rule, you will find like the direction in this area, the magnetic field in this area generated from the I1 is just into the page. We call it, we just use B1 to represent it. And using the right hand rule for forces, we can see that when I2 is in the same direction as I1, the second wire is attracted to the first wire. You can see, just use the right hand and this direction is your thumb direction, and your like index finger is go into the page, and then you can see the force direction is just from right to left. Yeah, point to the I1. Yeah, which means the second wire is attracted to the first wire. If they were in opposite direction, the second wire would be repelled. Yeah, this is just like we use the right hand rule and to get it. Yeah, and the magnetic field created by the wire with current I2 will also exert an attractive force on wire with current I1. The force on the two wires from Newton's third law action or reaction pair. Yeah, the force due to the magnetic field of the wires are directed in opposite direction and must have the same magnitude. Yeah, you can see here if the current in the same direction, it will attract with each other. If it has like a opposite direction, and it will like the repel like with each other. And yeah, this is just like according to the right hand rule, according to the like Newton's third law. Yeah, that makes sense to you? And yeah, and then the forces due to the magnetic field of the wires are directed in opposite direction, and must have the same magnitude, which means this will have the same magnitude with this one. Yeah, and this also have the same magnitude, but the same direction, but the opposite direction. Yeah. Okay. Yeah. let's talk about this example, finding the force between wires in jumper cables. You may have used a set of jumper cables connected to a running vehicle to start a car with a dead battery. Yeah, jumper cables are a matched pair of wires, red and black, joined together along their length. Suppose we have a set of jumper cables in which the two wires are separated by 1.2 centimeter along their 3.7 meter, like around 12 feet length. While starting a car, the wires each carry a current of 150 N in opposite direction. What is the force between the two wires? Yeah. According to our earlier discussion, the magnitude of the forces on the wires are equal. Thus, we only need to find the force on one of the wire. Yeah, let's suppose we want to find the red one, but the black one, the magnitude will be same. Okay, finding this force is a two-step process. And first, we will find the magnetic field at the position of the red wire due to the current in the black wire. Then we will find the force on the current in the red wire due to this magnetic field. Okay, firstly, we start by stretching the situation, noting distances and the currents as shown in the figure. Yeah, you can see we know the length is 3.7 meter and the current is 150 N and those two, just the distance is 1.2 centimeter. Okay, let's talk about let's use this equation. Yeah, the magnetic field at the position of the red wire due to the current in the black wire. We use this equation. Yeah, and we know this is the you just use the equation for the long straight line, and then you can calculate the if we want to find the force on the red one, we need to find the magnetic field generated by the black one. Am I right? For the black one, for the magnetic field generated by the black one, yeah, it's a long straight wire. So we use this equation, and yeah, and this d is just the distance between this red with the left with the black. So yeah, then we know the mu zero is a constant. The current is just the current in black one, and it is also 150, and this is the distance. Yeah, and then we can calculate the magnetic field is this one. Yeah, according to the right-hand rule for fields, the magnetic field is directed into the page. Yeah, you can see. Because this is for the you can use the right-hand rule to find the magnetic field generated by the black one. So you can see it should be going to the page. Yeah, from here. Yeah, use the right-hand rule we talked about in last class. That makes sense to you? Yeah. The magnitude of the force on the red wire is then we use this equation. It's ILB, and I we know that current L, and we know that the length and B, we know that we got it from here, and then we know the magnitude of the magnetic force, and then we can use the right-hand rule to calculate to get the direction. You can see here. Because this is the magnetic field direction, and this is the current direction. Yeah, the current direction is just this way. So which means the thumb should be pointed to the right, and the index finger should go into the page, and then the force should be goes to this direction. Yeah, you can use the right hand rule. That makes sense to you? Okay. The direction of the force can be found using the right-hand rule for forces. And the magnetic field at the position of the red wire is into the page, while the current is to the right. This means that the force on the red wire is in the plane of the page, directed away from the black wire. Thus, the force between the two wires is repulsive, as we expect when their currents are directed oppositely. Yeah, you can see. If you analyze that, you will find that the force between those two wires is repulsive. Yeah, does it make sense to you? Okay, let's continue and let's assess this result. These wires are long, close together and carry very large currents, but the force between them is quite small, much less than the weight of the wire. In practice, the forces between currents are not an important consideration unless there are many cores of wire leading to a large total force. This is the case in an MIR solenoid. Yeah, we will talk about later. Okay, and let's talk about this problem solving approach, like how to resolve magnetic force problems. Yeah. Yeah, magnetic fields exert forces on both moving charges and current carrying wires. But in both cases, the force can be found using the same approach. Yeah, although we talk about two different situations, the magnetic fields on moving charges and on current carrying wires, but they can be solved using the same approach. First, let's talk about the strategy. There are two key factors to identify in magnetic force problem. Yeah, the source of the magnetic field, the charge or currents that feel a force due to this magnetic field. Yeah, for the preparation, in magnetic force problems, the force, the field, and the wire or the direction of the moving charge can all point in different directions. So it is especially important to prepare a careful sketch of the situation. Yeah, you can sketch. Yeah, all you can draw all the situation, all the direction of force, the field, and the where, all the direction of the moving charge, and make it clearly. Okay. First, determine the magnitude and direction of the magnetic field at the position of the charges or currents that are of interest. In some problems, like the magnetic field is given. If the field is due to a current, use the right-hand rule for fields to determine the field direction and the appropriate equation to determine its magnitude. Yeah, we have some equation for different situation. Yeah, and you can use that equation. Next, determine the force this field produces, working with the charges or currents you identified previously. Use the right-hand rule for forces to determine the direction of the force on any moving charge or current, and use the appropriate equation to determine the magnitude of the force on any moving charge or current. And after you get the result, you need to assess the results. Are the forces you determine perpendicular to the velocities of moving charges and to currents? Yeah, are the forces perpendicular to the fields? Do the magnitudes of the forces seem reasonable? Yeah, you need to verify your answer based on those things. Yeah, does it make sense to you? Yeah, you also can find this problem solving approach in the textbook, page 816. Okay, let's continue to talk about the forces between current loops. Yeah, just as there is an attractive force between parallel wires that have currents in the same direction, there is an attractive force between parallel loops with currents in the same direction. Yeah, you can see there are some current loops. And then the long straight wire, if the direction is the same, and then they will be attracted with each other. If the current direction is opposite, and then there will be a repulsive force between parallel loops with currents in opposite direction. Yeah, that makes sense to you. Yeah, this is just the forces between current loops. And the field of a current loop is very similar to that of a bar magnet. A current loop, like a bar magnet, is a magnet dipole with a north and a south pole. You can see this is a bar magnet. Magnet field is a dipole field. You can see this is north and this is south. This is north, and the uh, the magnetic field should go out from north and go into the south, and it's just a dipole field. A field length goes into the south pole and come out of the north pole. And for a current loop has a dipole field. Yeah, you can see as well. Like as with the magnet, we assign loss and the source pole based on where the field lengths enter and exit. Yeah, for here it go out from this direction and then into this one. It's just similar this in this sorry oh, yeah, in this set is similar like a north pole, and in this set is similar like a north pole. That makes sense to you? Okay. Yeah, because the current loops have north and south pole, we can picture a current loop as a small bar magnet. Yeah, and here the north loop of this current pole is just this is north pole and this is south pole, and and uh, and for this like for this loop, and it those two have the same current, so this one is attracted to the source point of this loop. Yeah, that makes sense to you. So the north pole of this current loop, yeah, if there are this is for the situation like two current loops have the same current direction, and which means this is just like this, and this just like this, and those two, because it is like a opposite pole, so north and south, it will be attracted with each other. With each other. That makes sense to you. And for the opposite, like current direction, yeah, and this is just like north. This is north. This is south, and but this one is opposite. So this is north and this is south. So opposite, obviously, like it will have the repulsive force. That makes sense to you? Yeah, the north pole of this current loop, and this one is repelled by north pole of yeah this loop. That makes sense to you? Yeah, yeah. Let's check this question. Yeah, the diagram below shows slices through two adjacent current loops. Think about the force exerted on the loop on the right due to the loop on the left. The forces on the right loop is directed. Yeah, you can see since those two current loop has the same direction, so which means it should be attracted with each other. So for the right loop, for this one, this is the right one, it should the like force should go to this direction because it's attractive with each other. That makes sense to you? So which means it's to what? To the left. That makes sense to you? Yeah. So it's very obvious. So we need to choose A. Okay, let's talk about this one. This example problem, and a 10 centimeter length of wire carries a current of 3.0 N. The wire is in a uniform field with a strength of 5 multiple 10 power negative 3. Like this is just this direction, this value. Tesla. Yeah, as in the following diagram. What are the magnitude and the direction of the force on this segment of wire? Yeah, I think this one. First, let's use the right-hand rule to decide the direction. You can see the current direction. We just use the thumb to point to the current direction, and then use your index finger to the direction of magnetic field. Yeah, go into the plane, and then you will find the force will will point to the left. That makes sense to you. You can see it just like this. Yeah, and you just this is your current direction, and this is your like magnetic field direction. Yeah, go to the plane, and then this is the magnetic force direction. Does that make sense to you? Okay, let's continue. So, which means the direction should go to the go to left, and then for the force we use this equation I will be, and then we know the I is 3.8, and IO we know it is 10 centimeter length, so it's 0. Yeah, meter. Yeah, we need to use this one, and then we use. Oh, sorry, it is 10 centimeter. It should be 0.1 meter. Sorry, and then multiple the electric field, magnetic field. Then you can get the force. Yeah, this one is easy. I'm right. So use the just use the problem solving. Let me see where is the problem solving. No, this sorry. Let me find it for you. You know this. Yeah, we just talk about the problem solving steps. Yeah, just use that problem solving steps to solve those kind of problem. Yeah, we just talk about it. Where is it? Oh, here. Sorry. Yeah, you just use these steps. Problem solving approach like a 24.1. Yeah, to resolve all this problem. Yeah, for this one. For this one. Yeah. Okay. Where is what we talk about? Where is? Okay. Yeah. Oh, this one. Sorry. Yeah. And yeah, you just use the right hand rule to find the direction and use the equation to calculate the force. That makes sense to you. Okay, let's continue. Let's talk about the magnetic fields exert torques on dipoles. Yeah, this is a new thing for us. Okay, let's talk about that. Yeah, a curtain loop, which is a magnetic dipole, experiences a magnetic force due to a uniform magnetic field. You can see there is a unique magnetic field. Yeah, B is a uniform magnetic field, and here there is a current loop, and which means um, here will be a magnetic dipole. Here is a N, here is a S. That makes sense to you. And then because the field is uniform, the forces on opposite sides of the loop are of equal magnitude and therefore produce no life force. You can see this one. Yeah, this one, and this one, the magnitude will be equal and the direction is opposite. So, which means there is no net force like for this side. Okay, and the forces on the top and the bottom of the loop will rotate the loop by exert a torque on it. Yeah, since yes, for the top and the bottom, yeah, you can see here there is a angle. It's not like this is y. This is y. I'm right. So there is an angle. Yeah, this maybe it is just alpha, and those two just make the make the like a loop rotate. Yeah, rotate the loop by it will exerting a torch on it. That doesn't make sense. In a uniform field, a dipole experiments a torch, but no light force. Yeah, you can see the force. Yeah, because the force is it will be equal. Yeah, but it will like experiments a torch. Okay. Looking at the current loop from the set, the force F top. Yeah, this is the F top, and this is the F bottom, and act to rotate the loop clockwise. Yeah, which means this one. Yeah, because it will. This is electric field, magnetic field. Sorry, magnetic field, and which means and this one will like this force top and bottom act to rotate the loop clockwise. Yeah, because here and it will like because this is the uh yeah yeah this is just like this just we just like look at the current loop side from the side, and this one will you can see it will like make this loop go up, am I right? And this is go down, which means it will go up and make this rotate. Does it make sense to you? Yeah, you can this is like an angle between the loop and the field. Yeah, you can see it's just like this angle. Yeah, this is the field. That makes sense to you? Okay. Yeah, so the force F tops and F bottom acts to rotate the loop clockwise and into this direction because it will go to this direction, goes to, yeah, this is the axis of loop. Yeah, this is the angle, and this will go to this direction, yeah, clockwise. And the net torque is this one. Yeah, is the top torque and plus the bottom torque, and equal this one, and plus this one. Actually, the force actually is the same thing. Yeah, and here this is L is just the the length of the current loop. Yeah, this one. Yeah, this one. This one is the length. Yeah. So, and we use this equation. We can get this one. Yeah, that makes sense to you. Yeah. Actually, the torque equal what? The F, the force multiple the this torque distance. Yeah, torque distance. This is the torque distance, and then multiple the angle. Yeah, this is the angle. Yeah. So actually, those two is the force is the same, and then you can see we can get the total like a net torque is this one. That makes sense to you? Yeah. L square is the area of A of the square loop. Yeah, because A is just the side of this length of this square. Yeah. So, like the general result of the torque on any loop of area, we can use it, we can get this one. Yeah, here. Um, this is because this is area. Yeah, it's not like current or something. Yeah, this is current and this is area because L square. We just use A, like replace L square. Yeah, to tell you this is just the area. Okay, that makes sense to you. Okay, and then the torque depends on properties of the current loop. Its area A and the current I. Yeah, you can see if you observe this equation, this torque. Actually, it depends on the current, it depends on the area, it depends on the magnetic field, it depends on the angle. Yeah. So the torque depends on property of the current loop. 然后 the property of current loop is area and the current. And the quantity IA is the magnetic dipole moment and is a measure of how much torque the dipole will feel in a magnetic field. Yeah, you can see the magnetic dipole moment is represented as a vector that points in the direction of the dipole's field. A longer vector means a stronger field. Yeah. This is the orange one is the magnetic dipole moment. What is IA? I'm right. Yeah. If the dipole moment, magnetic dipole moment, a longer vector means a stronger field because IA, if IA bigger, which means the torch bigger. Am I right? Does that make sense to you? And it means yeah, a stronger field. Okay. Yeah, the torque depends on the angle between the magnetic dipole moment and the magnetic field. We talk about it. Yeah, the torque is maximum when theta equal 90 degree. It's obvious because this is the equation for the torque. And if this one is equal 90 degree, theta is equal 90 degree, which means this one is equal 1. Yeah, it's maximum. Otherwise, because we know the sin theta is always smaller or equal 1. That makes sense to you. Okay. Yeah, the torch is maximum when theta equal 90 degree. Yeah. And when the magnetic moment is perpendicular to the field. And the torch is 0 when theta, here it's just a typo. It is 0. Theta is 0. When the magnetic moment is parallel to the field, actually you can see we can use this thing. Yeah, what here the theta actually is just this is the y, so this is just the theta. Yeah, this theta, this is theta. Also, like the theta is also this. Yeah, if there is a line and this is the theta, it's those three are same. Yeah, if this theta equal 90 degree, which means if this one is just like this, actually the torque moment, the moment, the like a magnetic moment. Yeah, you can see magnetic moment actually is perpendicular with the surface of like a current loop. Yeah, so which means yeah, for this if it is in this situation, the like the current loop is just like a parallel with the magnetic field, but the moment just the perpendicular to the magnetic field. So in this situation, this is just the theta. Theta equal 90 degree. In this situation, and the like a moment, the magnetic moment is 90 degree perpendicular to the field, and the torch and the torque is maximum. And when it is 0, if the theta is 0, which means yeah, in this situation, yeah, it is 0, which means if the this is just in this in y, and which means there is no like a theta here. Am I right? So which means the moment, the like a electric moment, magnetic moment is just parallel with the magnetic field. So which means for in this situation, like the torque is 0. Yeah, that makes sense to you. Yeah, we can talk about this more, you to understand deeply. Yeah, here. Oh, sorry, I just need to clear it. Yeah, and you can see For this, a magnetic dipole will rotate to line up with a magnetic field, just as an electric dipole will rotate to line up with an electric field. Yeah, it's similar with like electric field. With the relationship between electric dipole and the electric field, you can see here there is a externally created magnetic field. Yeah, this one. And this one is the current loop. Yeah. And this is the magnetic dipole moment. Yeah, it's just like a perpendicular. For this situation, the theta equal 90 degrees. So which means the magnetic dipole moment perpendicular with the like magnetic field. Yeah, in this situation, the torque is maximum. Yeah, the dipole free to rotate. Yeah, will do so. It will free to rotate. And which means here this is the magnetic force. This is magnetic force. It will make the make the loop like a turn to this way, like a clockwise, run, and then after the theta become smaller. Yeah, you can see this if it run turns to this direction and it will go to this one, and then this is the magnetic dipole moment and theta smaller than 90 degree. Yeah, and as the theta decreases, the torch also decreases. Yeah, because you can see from this equation. Yeah, the theta is smaller, which means this one. Sorry. Yeah, which means this one is smaller. Am I right? Other like varieties keep the same. So which means this one will decreases. That doesn't make sense to you. Yeah, and if the torque is 0, which means here you can see the theta here is 0. Yeah, once the dipole is lined up so that the angle is 0. In this situation, the torque is 0, and then the current loop will keep still because there is no torque. That makes sense to you. Okay, let's continue. Yeah. For any dipole in a field, there are two angles for which the torque is 0. 0 or like 180. Yeah, you can see if for yeah, in this situation it is 0. Am I right? Yeah, but if it turns to this direction and flip, it is 180. It also, and which means the like moment will goes to this direction. It goes to this direction, but it's still like the theta is 90 degree because this is not 90, 180. Yeah, and but in this situation the torque is still 0. Yeah, when theta is 0 and it is stable, the dipole will stay in this configuration. Yeah, when theta is 180, it is unstable. You can see in this situation. Yeah, if the torque moment, if the magnetic dipole moment goes to this direction, yeah, and it will not like it will not stable. Yeah, the slightest rotation will result in a torque and rotate the dipole until it reaches to the theta equal 0. Yeah, this situation has a gravitational analog, an upside down pendulum. Yeah, the unstable alignment of the dipole will has a higher energy and will rotate downhill to the stable equilibrium of lower energy. Doesn't make sense to you? Yeah. Okay. And this is like here. This is the gravity direction, and here there is a pivot point. The pendulum balancing upside down, and the magnet aligned opposite the field are in unstable equilibrium. a small notch. You can see here if the this is the external like a magnetic field. Here this is the magnets. Yeah, is a compass. Then you can see it should like from north to south. Am I right? And this will like make this compass notch. Yeah, this one is it's not a stable like equilibrium. But if it is just opposite, which means this ice will attractive to this one, and this if sorry, let me make it clear. If you opposite it, like flip it, they will just like this, and this is the N, this is the S. And then because here is the N, here is S, it will be very stable because this will attract it by this direction. Does it make sense to you? Yeah, but this one, it's not stable. Yeah, that makes sense to you? Yeah. Okay. Then this situation, and it will lead to a torque. It will lead to a torque that will cause a rotation that will continue rotate until it become this situation. This one is N, this is S, and that makes sense to you. Yeah. Okay. And the condition of the stable equilibrium is reached, yeah, until they reach to this situation, which means we know this is NS, yeah, from N to S. Here is S to N because it's attractive to N. So which means this situation will be very like stable. Yeah, for the this one is just the comparison. Yeah, for the gravity. Yeah, and we know like here if there is a pivotal point, there is a ball, and it will not be stable in this situation, and it will like go down, and until like it will keep in this situation. Does it make sense to you? Yeah, it's similar with the gravity thing. Yeah, the magnetic thing. Okay, let's review some question. If released from rest, the current loop will, yeah, here which means when the this is because this is like the current loop, which means the let us to find the like magnetic moment. Let us find the like magnetic dipole moment. Yeah. Yeah, magnetic dipole moment is just like we just use the yeah. Also, we can use the right hand rule to find the force, and then we can decide how this current loop move. You can see for this one, the current direction is into the page. Am I right? And then we use the thumb go to the page, go into the page, and then the the index figure go to the left, go to right, because the magnetic field go to the left. So which means the force will be where? Yeah, because it is yeah, this one in this point, and the current is go out of the plan. Am I right? So which means the index direction is go to the index figure is go to the magnetic field direction. It is go to the right. So the force should up. That makes sense to you. You can see. Let me show my figure to you. Yeah, just this one. Yeah, this one. Yeah, this one. This is just like a go outside of the plan, and this one is just go to the magnetic field, and then you can see this one is a magnetic force. Yeah, let me. Okay, And we use the right-hand rule for the same situation here. And because here you need to opposite your like thumb figure. Yeah, because it is go into the uh go into the uh plane. And then the magnetic field is the same like uh same direction. And so then you can use the right hand. Yeah, let me show my finger. Yeah, you can see just for just now, and it's just like this. Am I right? So the like on the point on the right point on the on the right point the force is up, but for the left point, the like direction of the current is opposite. So this one is just opposite. You just like opposite your like which means this one will go into the plane and this direction is the same, so the force should be down. That makes sense to you? Yeah, so which means this here is down, so which means it will what counterclockwise. Yeah, it will rotate counterclockwise. That makes sense to you, so the answer should be D. Okay, yeah, you can see, yeah, you can use the right hand rule to find the force and then, yeah, to decide which direction it will be. And let's talk about this example. Yeah, does the loop rotate? Okay, and you can see like two nearby current loops are orientated as shown in the figure. Loop 1 is fixed in place. Loop 2 is free to rotate. Will it do so? Yeah, does it make sense to you? Yeah, does it make sense to you? Okay, let's talk about this one. And yeah, you can see like the current in loop 1, this is current loop 1, and generates a magnetic field as a figure showing. Yeah, yeah, this is the uh as a figure showing because this one will generate the field. This is will generate, yeah, because this is just the this is a loop 1 and it will generate a magnetic field like this. And the the field of loop 1 is upward. Yeah, you can see if here is a loop 2, it will affect loop 2, so will like upward. That makes sense to you? Yeah, yeah, not just see here, because you want to analyze the loop 2. Yeah, so you need to find how the loop 1 affect loop 2. So you can see here, this is the magnetic field generated by loop 1, but affect loop 2. Does it make sense to you? Yeah, it is upward as it passes loop 2, because the field is perpendicular to the magnetic moment of loop 2. Yeah, the field exerts a torque on loop 2 and causes loop 2 to rotate until its magnetic moment lines up with the field from loop 1. Does it make sense to you? Yeah, which means the loop 2 will rotate. And these two loops align so that their magnetic moments point in opposite direction. Yeah, we can think of this in terms of their poles. When aligned this way, the north pole of loop 1, yeah, actually, this one is which this one is north, this one is south. Yeah, the north pole of loop 1 is closest to the south pole of loop 2. Yeah, you can see for the loop 2, and it should this is the source, this is the north. Yeah, so the north node loop 1 is closest to the south node loop 2. This makes sense because these opposite poles attract each other. Does it make sense to you? Yeah, so the loop 2 will rotate counterwise, which means this direction, until its magnetic moment lines up with the field. Okay. Let's talk about MRI. Yeah, magnetic resonance imagine. Actually, this is an application for the magnetic fields. Yeah, and magnetic resonance imaging is a modern diagnostic tool that provides detailed images of tissues and structures in the body with no like radiation exposure. The key to the imaging technique is the magnetic nature of atoms. The nuclei of individual atoms have magnetic moments and behave like magnetic depots. Atoms of different elements have different magnetic moments. A magnetic field exerts different torques on different kinds of atoms. Yeah, this is just how can we use magnetic moments and magnetic depots for the magnetic resonance imagine MIR. Yeah. Okay, if we consider only the hydrogen atoms in a person's body, the single proton of each hydrogen atom will align either with the field, yeah, the low energy state, or opposite to the field, the high energy state. The energy difference depends on the magnetic moment of the proton and the strength of the magnetic field. Yeah, you can see here. This is the a proton's magnetic moment. Yeah, this is a proton's magnet can line up in two orientations with two different energies. Yeah, the energy difference between two states is delta. Yeah, this is one, this is two. The opposite of the field, this is with the field. There will be a difference, energy differences. Yeah, and a probe field precisely turned to the proper energy flips the atom depots from the low energy state to the high energy state in an MIR. A strong signal indicates that many of the atoms of interest are present. Different tissues have different concentrations of atoms. A record of the density, various position of measurement gives an image of the structure of the interior of the body. You can see this is MR picture image. It's very like clear for us, am I right? Yeah. In an electric motor, yeah, a loop of wire called the armature is free to rotate in a strong magnetic field. A current in a loop causes it to feel a torque. The loop rotates to align itself with the external field, but the commutator reverses the current direction in the loop every 180 degrees. When the loop is close to a stable configuration, the current switches, so the loop continues to rotate. Yeah. This is for the electric motors. Yeah. Another application for the magnetic moment. And yeah, here, this is electric motor. Yeah, the forces on the loop result in a clockwise torque. And yeah, the commutator reverses the current in the loop every half circle so that the torque is always clockwise. Yeah, that makes sense to you? Okay, let's check this question. A current carrying loop sits between the poles of a magnet. Magnetic forces rotate the loop as shown in the figure. From the point of view of the north pole of the magnet, the current in the loop is, yeah, you can see, like because yeah, we know like this is N, this is S, so we can draw the magnetic field direction. This is the magnetic field direction, and then we use the right hand rule to this is the, because this is the rotation direction. We know the rotation, so this is the force, and this is the force. That makes sense to you. So then we use the right hand rule to get the current direction, like for this point, we this is A, this is B. For port A, and you can see the middle figure should go to like a should go to like a red, and the index figure should go to red because it is a magnetic field direction, and the middle figure should go down, and so the current direction should goes into the page. Am I right? So which means it should be like this, and then which use the right hand direction, use hand like a rule also to on the B, and you will find it just opposite. Yeah, you will find it's just opposite. So you can see it the current direction is just go out of the um go out of the plane. If you from the point of view of the north pole of the magnet, which means it should just like this. Am I right? So which means it is counterclockwise. That makes sense to you? Yeah. So the answer should be B. Yeah. Just use the right hand rule to find the current direction, and then you will know what's the current in the loop. Yeah, that makes sense to you. Okay, let's talk about this one. This example problem. A current carrying loop sits between the poles of a magnetic. Which way will the loop rotate? Make the determination by considering the forces on different parts of the loop. Then, by considering the pole structure of the loop, what will be the loop's equilibrium position? Yeah, first, I think this is just a similar thing. Yeah, we talk about a lot for those kind of problem, and this is magnetic field direction, and we know the current direction. So yeah, so like you use the right hand rule, and just yeah, you can see yeah, if you use the right hand rule, and you will know like it's just yeah, it's just like this is up. Yeah, the force this is up, this is down, and you will see, and it is a loop will rotate counterwise. Yeah, the equilibrium position is a loop aligned with the poles with the branch with the current into the page on the left near the north pole. Yeah, so which means the equilibrium should like should like this. Yeah, does make sense to you? Yeah, and the branch with the current end of the page on the right near the uh south pole. Yeah, that makes sense to you? Yeah, I will left this question to you, and you can think about this one. And if you have any question, just let me know. Actually, we have already talked about a lot for this kind of problem. Okay, let's continue. Okay, we will then finally we will talk about magnets and magnetic materials. Okay, yeah, materials that are strongly attracted to a magnet and that can be magnetized are called ferromagnetic. Yeah, magnetism at uh, atomic level is due to the inherent magnetic moment of the electrons. Yeah, you can see the arrow that represents the inherent magnetic moment of the electron. Yeah, actually, those like a magnetic moment, inherent magnetic moment, like makes these materials have the magnetism. Yeah. Okay, in most atoms with many electrons, the electrons occur in pairs with magnetic moments in opposite direction. You can see, yeah, and unpaired electrons. Yeah, these are some like unpaired electrons are able to give an atom a net magnetic moment. Yeah, because it is now paired, so the net is now zero. Yeah, there will be a net magnetic moment. For most elements whose atoms have magnetic moments, the moments are randomly arranged when the atoms like join together to form a solid. So there is no net magnetism. Yeah. Yeah, which means like for most elements, yeah, like for example, copper or paper or water, yeah, whose atoms have magnetic moments. The moments are randomly arranged when the atoms join together to form a solid, so there is no net magnetism. Yeah, but for ferromagnetic materials have atoms with net magnetic moments that tend to line up and reinforce each other. You can see this, yeah, for the most material, yeah, most elements, it's just the atomic magnetic moments like due to unpaired electrons pointing in randomly direction. Sorry. Yeah, uh, random direction. The simple has no net magnetic moments. Yeah, just like this. Yeah, but for the ferromagnetic materials, yeah, have atoms with yeah like with net magnetic moments that tend to line up and reinforce each other. You can see it's just similar like this. Yeah, the atomic magnetic moments are aligned. The simple has north and south magnetic poles. You can see. Yeah, the alignment of moment occurs in only a few elements and alloys. Yeah, a piece of such a material has a north and a south magnetic pole, generates a magnetic field, and aligns parallel to an external like magnetic field. It's a magnet. Yeah. In a large sample of iron, the magnetic moments will be lined up in local regions called domains, but there will be no long-range ordering. Inside a domain, the atomic magnetic moments will be aligned, but the magnetic moments of individual domains will be randomly orientated. The individual domains are quite small, on the order of 0.1 meters or so. So a piece of iron, the size of a nail, has thousands of domains. Yeah, you can see. This is the magnetic moment of the domains tended to cancel one another. The sample as a whole process, no net magnetic moment. Yeah, this is a magnetic domain. This is a this yeah different magnetic domain. Yeah, and the atomic moments are lined up within each domain. Yeah, like each yeah for each domain. Yeah, the atomic moments are lined within each domain. Yeah, but different domains. Yeah, like yeah different domains tend to cancel one another. Yeah, because it's randomly arranged. Yeah. And when you bring a magnet near a piece of iron, as in the figure, you can see if you like the magnetic field of the magnet like penetrates the iron and creates torques on the atomic magnetic moments. You can see here. Yeah, this is unmagnetized piece of iron. Yeah, this one. And initially, the magnetic moments of the domains cancel each other. There is no net magnetic moment. But if you like bring a magnet near a piece of iron, and then you can see here this one. You put a bar magnet near to the magnet near to the like a piece of iron, and the domains aligned with the external field becomes larger at the expense of domains opposed to the field. The iron will have developed an induced magnetic moment. You can see the magnetic field from a magnet causes favorably oriented domains, yeah, shown in gray, to grow at the expense of other domains. Yeah. And the resulting domain structure has a net magnetic moment that is attracted to the magnet. The piece of iron has been magnetized. Yeah, you can see if there is a magnet, it will make the those three like has the same direction, maybe not this one, not this one, but which means there will be a net magnetic moment. The magnetic moment will not be zero because yeah, maybe some in the same direction, which means this direction has a stronger like a magnetic moment. Doesn't make sense to you? Yeah, there will be a net magnetic moment. Okay, now we have an explanation of how a magnet attracts and picks up like a ferromagnetic objects based on three facts. The first one, electrons are microscopic magnets due to their inherent magnetic moment. The second one, in a ferromagnetic material, these atomic magnetic moments are aligned ridges of aligned moments from magnetic domains. The third one, the individual domains shift in response to an external magnetic field to produce an induced magnetic moment for the entire object, which will be attracted by the magnet that produced the orientation. Yeah, that makes sense to you. And you can see, like when a piece of iron is near a magnet, it becomes a magnet as well. Once a magnetic field is taken away, the domain structure will return to where it began. The induced magnetic moment will disappear. Yeah, very strong fields can cause permanent orientation changes to some domains, which will permanently magnetize the material. Yeah, sometimes if you put some like iron to a permanent magnet for a long time, and then those iron will become a magnet. Yeah, you can try it. And I want to explain one thing. Yeah, we talk about the if the iron the iron like the North Pole can attract iron, and also the North Pole also can attract iron. And that makes sense. Do you remember that? Yeah, that's because yeah, you can see for this situation, the North make the this like a magnetic moment in this direction. If you opposite it, like this is as is yeah, for example, yeah, and then those kind of direction, yeah, will maybe this kind of yeah, it will make this kind of like a domain goes to this direction. Yeah, and then it will become a magnet. Yeah, doesn't make sense to you. That's the reason why the north can attract the ferromagnetic material. Also, the south pole can attract that one. Doesn't make sense to you. Okay. Yeah, induced magnetic moments are used to store information on computer hard disk drives. The magnetic field of a tiny switchable magnet, yeah, changes the orientation of the domains of the magnetic coating on the surface of the hardware. This encodes information which can be read by small probe sensitivity to the magnetic field of the tiny domains. Yeah, read ahead. Yeah, this is just an application for the like a ferromagnetic material. Yeah. Yeah, this is what we just talked about. And yeah, here is a cross section of magnetic coating on hardware. And this is this arm. Yeah, this arm rapidly moves the right and like right head to the required position over disk. Actually, I think you guys maybe seldomly see this now. Yeah, because it have already integrated into a computer. Yeah, like a laptop. Yeah. You can see here, 0 are stored as one longer magnet, and 1 are stored as 2 short magnets. Yeah, you can see this is we know like the data stored in laptop computer is 1010. There's like the binary, you know that. So here the 0 is just stored as one long magnet, and ones are stored as 2 short. Yeah, this is how the disk can be saved, can be used to save the data. Yeah, does it make sense to you? Okay, let's talk about the electromagnets. Yeah, the magnetic domains in a ferromagnetic material have a strong tendency to line up with an applied magnetic field. A ferromagnetic material can be used to increase the strength of the field from a current carrying wire. A solenoid would wound around a piston of iron will be magnetized when a current is passed through the wire, creating an electromagnet. Actually, yeah, an electromagnet can produce a field that is hundreds of times stronger than the field due to the solenoid itself. Actually, we will talk about electromagnet in next chapter. Yeah, in next 2 days. Yeah, don't worry. Yeah, we will talk about more about this part. Yeah, you also can view the video for this part. And okay, if you have any questions, just let me know. Yeah, this is what we talk about in today's class. Actually, do you remember what's the main things we talk about in today's class? Actually, yeah, we just focus on the magnetic forces. Yeah, do you remember that? Yeah, last class we mainly focus on magnetic fields. Today we will just focus on the magnetic forces. Yeah, and we talk about how to use right hand to get the direction of the magnetic forces and how to use the equations to calculate the magnetic forces. Yeah, and yeah, and something related to the magnetic forces. Yeah, this is what we in this class in today's class. Yeah, and okay, we have already finished the chapter chapter 24. Yeah, and let's do a summary. Yeah, you also can view this video for some like tutor solutions. Yeah, I will now play the video here. Okay, let's begin to summarize it. Yeah, and there are some general principles. Yeah, for the source of magnetism, we know that like magnetic fields can be created by the electric currents. Yeah, we know that. Also, like all the permanent magnets, of course. Yeah, the permanent magnets can create the magnetism. Also, the electric currents create magnetism. Yeah, the most basic unit of magnetism is a magnet dipole. Yeah, which consists of a north and a south pole. Yeah, this is such, for example, this one. Yeah, and yeah, actually the electric current also like it is can form a magnetic dipole, and this is S. Doesn't make sense to you? Okay. Yeah, this is three like a basic kinds of dipoles. Yeah, this is a current loop. Yeah, we talk about that. This is a current loop, and this is a permanent magnet, and this is a atomic magnet. Yeah, this is what we talk about in today's class. Yeah, inside some material, some object, there will be a atom, atomic magnet, and this is a magnetic moment. Yeah. Okay. Let's talk about the consequences of magnetism. Yeah, magnetic fields exert long-range forces on magnetic materials and on moving charges or currents. Yeah, we talk about this. Yeah, unlike poles of magnets attract each other, like poles repel each other. A magnetic field exerts a force on a moving charged particle. Yeah, parallel wires with currents in the same direction attract each other. When the currents are in opposite direction, the wires repel each other. Yeah, magnetic fields exert torques on magnetic dipoles and align their axes with the field. Yeah, this is what we talk about in today's class. Yeah. Okay. And we also talk about something about like magnetic fields. The direction of the magnetic field we can use is the direction in which the north pole of a compass needle points. Yeah, and due to the current can be found from the right-hand rule for fields. Yeah, the strength of the magnetic field is proportional to the torque on compass needle when turned slightly from the field direction, and it is measured in Tesla. Okay. Also, like we talk about something about magnetic forces and torques. The magnitude of the magnetic force on a moving charge depends on its charge. Yeah, its speed and the angle alpha between the velocity and the field. Yeah, this is what we talk about in today's class. The direction of the force on a positive charge is given by the right-hand rule for forces. Also for the like a negative charge, and you just like this the like force direction will be opposite with your finger. Yeah, just remember that. Okay. The magnitude of force on a current carrying wire perpendicular to the magnetic field depends on the current and the length of the wire. Yeah, this is the equation for that. And the torque on the current loop in a magnetic field depends on the current and the loop's area. I think it's just a miss and loop's area and how the loop is oriented in the field. Yeah, this is what this is the equation to calculate the torque on a current loop. And then we talk about yeah, fields due to common currents. If there is for the long straight wire, and this is the equation to calculate the magnetic fields. And for the current loops, and this is the like a magnet equation for that. If there is some like a stack of current loops, like this one, this one, this one, but the length is smaller than R, this R, yeah, and the B and the like a magnetic field should equal Ni divided R2. Yeah, do you remember that? And for the solenoid, and this is equation for the solenoid. Yeah, and this is just the length for this solenoid. Yeah, okay. And then we talk about some charge particle motion. And there is no force if velocity is parallel to like a magnetic field. We talk about that. And if like velocity is perpendicular to magnetic field, the particle undergoes uniform circular motion with radians. Yeah, you can calculate the radians using this equation. Yeah, this is this is the mass of the particle, and this is the velocity, and this divide, and this is the charge, and this is a magnetic field. You can use this equation, and you also can find this on in the page. This one, okay. Okay, we also talk about stability of magnetic dipoles. A magnetic dipole is stable in a lower energy state when aligned with the external magnetic field. It is unstable in a higher energy state when aligned opposite to the field. The probe field of an MIR scanner mirrors the flipping of magnetic dipoles between these two orientations. Yeah, we talk about this. And yeah, this is some applications. Also, we talk about some other applications, some like a motor and a magnetic motor. Yeah, you can review it if you want. Yeah, this is what we talk about in this chapter, mainly focus on the magnetic things. And most important thing is just magnetic forces and the magnetic fields. Yeah, just remember that. And yeah. Okay, we have already finished the chapter 24. And if you have any question, just let me know. Okay, thank you. See you. Bye.